Hello, everyone, and welcome to our NanoFrazor webinar series. Today, we'll be having our last installment of this year's webinar series, and we're very happy to welcome Giorgio Zambito for his talk. Before we move to Giorgio's webinar, I would like to share a few slides about our latest innovation, the next generation NanoFrazor system. And I'd like to remind you all that the webinar session today will be recorded. So we will be recording the webinar session, including the few slides I will show you in a minute. And at the end of the session, we will have some time allocated for a question and answers session with Giorgio directly. And this Q&A session will not be recorded, so you are welcome to then open your cameras again for the Q&A session. Simply raise your hand if you have any questions, and you'll be able to ask Giorgio these questions directly. All right, so I'll introduce myself. My name is Jana Chaaban, and I lead the Process and Applications Laboratory at Heidelberg Instruments Nano, based here in Zurich, Switzerland. Thanks again for joining the webinar today. In the next slides, I'll give you a brief overview of our latest system that we've launched this year, the next generation NanoFrazor tool. And I'll discuss how this tool is ushering in a new era of thermal scanning probe lithography with a particular emphasis on parallelization and automation. But first, a quick overview of our history. So the NanoFrazor technology originates from the IBM Research Millipede project, which ran over quite a few years at IBM Research in Zurich. In 2018, we joined Heidelberg Instruments, and at the moment we are 25 employees based in Zurich, working on both the development and the production of the NanoFrazor technology. This year, we've launched our latest system, the next generation modular NanoFrazor, which I will give an overview of in this talk. Our newest system is highly modular, flexible, and also 10 times faster. So one way we're tackling parallelization and increasing throughput with the system is by introducing an array of cantilever tips, the so-called decapede, which features not only one heated tip for the patterning, but 10 tips working in parallel. And these are all fabricated wafer level, so each tip is reproducible and similar to the one next to it. We've also made some improvements to our electronics. They are now faster, lower noise, and highly scalable. And we've also updated our packaging and interfacing of these cantilevers. So instead of using tweezers to pull in and pull out the cantilever tips, now they come already pre-packaged on a PCB, and as you can see in this video, they're quite easy to insert and remove from our NanoFrazor tools. When we put all of these aspects together, we get the 10 tips working in parallel. So here we see how our direct write technology is working through this screenshot of our NanoFrazor software. On the right side, you see an optical microscope view from our software of all 10 tips patterning on a sample. And on the left side, you see the live topography image of what we are writing being slowly built up. Here at the bottom, you see the profile that is being written. And as you can tell, it's being shown in a live manner. So you have directly the option to see the quality of your designs and how reproducibly we are writing grayscale features in this case. The blue line is the target depth and target design, and the red line here in the profile is the red design, and they're following each other quite well. In this particular example, all 10 tips are writing the exact same grayscale image, which I'm sure you all recognize. But actually, each tip is controlled independently and it's biased independently. This means that we can have each tip patterning a completely different design, as is exemplified here. This could be one tip for a 2D design, another for a grayscale design, and all of these would be working in parallel, also in combination with our integrated laser writer head for much faster throughput. Our newest system is also highly modular, so with the same NanoFrazor-based system, you could have the single-tip writing, all 10 tips writing, or also the laser writer head writing. In addition to flexibility, the newest NanoFrazor is highly modular and comes in many different configurations. On the left side, you see the tabletop system, which occupies the least amount of footprint in the lab. Next to it, you see the NanoFrazor in its own special housing, which limits the outside noise and provides a better environment for writing. And on the right side, you see the NanoFrazor system, which is integrated in a glove box environment. And this is mostly useful for handling samples that are sensitive to oxygen exposure. If you visit our website, nanofrazor.com, we have a configurator on it where, after you answer a few simple questions about your research and applications, we can advise you on the best NanoFrazor configuration for your needs. This was all from my side. I wanted to also highlight the exciting NanoFrazor webinar series that we've had over the last few months. We had 5 speakers join us from renowned research institutes around the world. And today we're very happy to welcome Giorgio Zambito. And I'd like to also highlight that all of these NanoFrazor webinar talks are uploaded on YouTube, and we'll be able to send you the recording of all the webinars very soon. So without much delay, I would like to welcome Giorgio Zambito with us today.
Yeah, hi. Thank you, Jana, for introducing me, and thank you also for the invitation. And okay, so I think that I might start sharing the screen.
You can share, and while you're sharing, I'll give a brief introduction to you as well. So Giorgio graduated from physics from the University of Genoa, and during his studies, he focused on large area growth and nanomanipulation of 2D transition metal dichalcogenides, or TMDs. And he went on to pursue his PhD research, where he integrated thermal scanning probe lithography with the NanoFrazor, together with TMD growth. And with both these technologies, he looked to develop deterministic nanocircuitry and also grayscale engineered layers, which we'll hear more about today. So, Giorgio, please go ahead. We're very excited to hear your talk.
Okay, thank you again for the introduction. And so today in this talk, I'm very happy to be able to have the opportunity to share with you some of our results dealing with the thermal scanning probe lithography and two-dimensional semiconducting materials. So in the physics department in University of Genoa, we have had the opportunity to work to play, let's say, with the thermal scanning probe lithography since 2020, since when we acquired a NanoFrazor Scholar, which you see here in this image in our facility. And before diving into the main topic of this presentation, I'd like to give you like a quick hint to other application that our group and other group in University of Genoa have been working on dealing with thermal scanning probe lithography. So, for example, a couple of works that we have worked on deal with plasmonics, and thermal scanning probe lithography has had the capability to give advantages in terms of fabrication of plasmonic nanostructures. So, for example, in this couple of works, we have worked on the fabrication of plasmonic nanostructures on one side of transparent substrates embedded with conductive transparent oxide that can be able to sustain plasmonic resonances while maintaining optical transparency. And also thermal scanning probe lithography allowed us to fabricate in a non-invasive approach plasmonic nanostructures on top of monolayer transition metal dechalcogenides, such as molybdenum disulfide. And if you want to give them a shot and check them out, here I attached the links to these two works dealing with plasmonics. And also another field where the NanoFrazor can give some advantages is dealing with flat optics. So the capability to fabricate metal lenses with the sub-wavelength features. And for example, in this work, we employed the NanoFrazor lithography to achieve spectral tuning of block surface waves, and with the controlled behavior depending on a controlling laser light, for example. And this is also a field where having the capability to embed this kind of metal lenses in a condition where all other techniques such as electron beam lithography fail can be very useful. And also, as a later work, we have been dealing, this is actually a work that is still to be published. Thermal scanning probe lithography is being implemented for the fabrication of high-resolution metal electrodes on insulating substrates to allow measurement in terms of thermoelectric transport. So here in this case, it's a kind of measurement and of fabrication that usually has to rely on optical lithography, and hence that like kind of limits the level of resolution that you can achieve when you fabricate metal electrodes. And as a consequence, the capability to perform a similar lithography but a higher resolution level, thanks to the NanoFrazor, can also be another kind of advantage that this technique gives you. So in this presentation, I will focus on the application of NanoFrazor to work with two-dimensional semiconducting materials such as transition metal dechalcogenides. So first of all, why are we interested in two-dimensional materials? I mean, there are plenty of reasons that should push you to pursue the application of two-dimensional materials, but why are we interested in semiconducting 2D materials? Well, these are atomically well-defined materials that present in the form of well-defined atomic layers, and we know plenty of classes of 2D materials. And among these, the one of transition metal dechalcogenides, or TMDs, possess a semiconducting behavior. But also they present optical absorption coefficients that are rather high. And as you can see, they are competitive or even better than more conventional semiconductors, such as silicon, of course, which is the most consolidated and well-known material in the semiconductor manufacturing industry. And also, another peculiar aspect of these materials lies in the fact that they possess an electronic band structure that is dependent on the number of layers that you consider. So, for example, for molybdenum disulfide, which is probably the most known and most studied semiconducting transition metal dechalcogenide, you have a direct to indirect band gap transition when you go from a single layer to a two or more layer configuration. And also quantitative dependence of the value of the energy band gap, depending on how many layers you consider. So there are a lot of possibility to tune, to exploit these materials, which possess, among all their properties, this kind of interesting behavior. And for these reasons, they are promising building blocks for a new generation, a new paradigm in terms of device that involve light-matter interaction in the visible range, and hence for devising optoelectronics or even photovoltaic configuration. So, given the fact that we may be interested into semiconducting 2D materials, we have to somehow first obtain your starting material. And to do that, generally, you can rely on two main paths. So the first one is mechanical exfoliation, which is, we may say, the most known way to obtain layered materials. And this kind of approach, which is the same that was exploited for first graphene isolation in 2004, is kind of easy to perform, and it gives you very good crystalline quality material, but you are kind of limited in terms of areas, generally at the microscale. And as a consequence, is not really suitable for creating replicable devices, replicable geometries in an on-demand fashion. And for these reasons, to overcome this limitation, people are making effort to develop larger approaches, such as chemical vapor deposition. And these processes allow you to grow extended layers of materials such as transition metal dechalcogenides, but you have to involve high temperature processes, and there are many parameters involved in these kind of processes, and it's kind of even difficult to replicate these results from one facility to another, for example. But anyway, whether you choose to rely on mechanical exfoliation or on CVD approaches, then you are generally interested in manipulating transition metal dechalcogenides. For example, for achieving the ability to fabricate replicable and on-demand geometries. So in this context, for example, we have worked on the combination of thermal scanning probe lithography technique together with a custom approach that we developed for the large area growth of transition metal dechalcogenides layers, which deals with ion beam sputtering using a DC defocused argon ion beam. And with this kind of process, we were able to obtain macroscopically extended layers of materials such as molybdenum disulfide and tungsten disulfide that, as you can see, possess extended areas in the range of the centimeter square. And if you're interested into the growth approach, the growth process, you can check out this work that was published last year that contains some more details about the growth process. So this kind of growth process combined with the bilayer liftoff by thermal scanning probe lithography allowed us to obtain a condition where we are able to homogeneously cover the whole substrate after t-SPL patterning, and after liftoff of the polymer mask, we are left with our nanogeometries, nanocircuits made of MOS2, for example. And as a consequence, we go from something like this. This is our facility logo embedded in PPA, as seen from the imaging capabilities of the NanoFrazor, and the resulting sample after the process I described you, where these darker regions observed by scanning electron microscope are actually made of molybdenum disulfide. And that allow us also to get deterministic placement and replicability of these complex geometries, as you can see, which is something that usually with mechanical exfoliation is kind of difficult to achieve. So since this is a NanoFrazor webinar, I think it's also interesting to stress another capability given by this kind of technique, which is the overlay lithography. So basically, the idea is that we can exploit the same tip that we use for lithography, but in a colder configuration, so without inducing any patterning on the polymer layers, to detect underlying objects, such as these two MOS2 nanofingers that we previously fabricated, as previously discussed. And directly after locating them without the use of any alignment marker, like it would be needed via electron beam lithography, we can align a geometry of our choice, just as like this black square representing a common electrode to these two nanofingers, and proceed with metal deposition and liftoff to actually obtain a device configuration. And in this specific case, we exploited this very simple device configuration to conduct a conductive AFM characterization measurement, which allowed us to observe, along with topography, also resistance and current maps, which allowed us to extrapolate an estimate of the resistivity of this material, of our MOS2 nanofingers and nanocircuits, which lie in line with the other results dealing with CVD-grown TMDs. But the point is that, as I said, once we have chosen how to obtain our material, we may be interested in manipulating their shape. And that is not just something that we want to achieve to obtain replicable geometries, but maybe we are interested in tailoring their optoelectronic behavior. And in this context, strain engineering has been proven to be an interesting way to tailor, to change the properties of this peculiar material. And so strain engineering is a word that is generally used to identify this way of tailoring properties of materials in general, and in this sense, in this specific case of two-dimensional materials. And it has been proven that when you apply a mechanical stress to the crystal lattice, of course, you change the properties that arise from the presence of a crystal lattice. And for example, it has been proven, it has been shown that it can induce an improvement in carriers mobility, in transistor configuration. You can modulate photoluminescence intensity, induce wavelength shift, even localizing photon emission, or for high degrees of strain, even inducing semiconducting to metallic phase transitions. The point is that in this context, the majority of examples are generally dealing with uncontrolled geometry of these materials. So maybe with implementing rough substrates or flexible substrates that are macroscopically bent, or AFM-assisted bending on nanomembranes. And anyway, all very interesting fundamental studies that do not allow to have a high degree of control on the geometry that you are implementing, especially if you want to achieve very high resolution in terms of geometry control. And so in this context, the use of thermal scanning probe lithography, and more specifically of grayscale lithography, is very interesting, and it is very appealing for this kind of study. And for example, this is a work that has been published last year, very interesting, from the EPFL group in Switzerland, which I suggest you to check out if you are interested in this kind of topic, dealing with grayscale lithography by NanoFrazor and two-dimensional materials. So in this context, I will show you how we exploited grayscale lithography by NanoFrazor to fabricate faceted patterns, and how we employed this kind of fabrication to work with the materials. So just to recap, if you're not familiar with the idea of grayscale lithography by NanoFrazor, by thermal scanning probe lithography, the idea is that the central part of the cantilever of the NanoFrazor works as a capacitive platform. This means that if you employ a conductive substrate, you are able to gain a high degree of control and high precision in terms of depth, not only lateral resolution. This means that you can devise and project some three-dimensional landscape, and you can reproduce them on the nanoscale with this kind of approach on conductive surfaces. And in our case, we exploited grayscale lithography to achieve patterning of faceted patterns with sub-micrometer periodicity. So basically, we are able to obtain landscapes like this, where we a priori decide the tilting of the facets. So for example, in this case, we have a 25 degrees tilt on one side of the facets, on the left side, and 15 degrees on the other side. And what you can see from this image is that we have a really high reliability of the process, because what you see on this first image is in light blue bottom part of the image is actually the design as it is fed to the NanoFrazor, while in the top part overlaid to the first image, you see what we actually get through the imaging capabilities of the NanoFrazor, demonstrating that we actually are able to replicate these geometries with a very high reliability. And also by the slopes distribution, which is basically an histogram of the first derivative of the topography image that I show here, we see three main peaks representing the flat areas, or also reproduced via NanoFrazor lithography, but also the presence of two peaks representing the left and right facets. And this is also observed by the polar dispersion of the facets, where we see the presence of these peaks, again relatable to the presence of left and right facets, and also we see the fact that they are actually distributed horizontally, which means that we actually have the tilting of the facets along the x-axis. So given this capability to perform lithography of faceted nanopatterns, we started kind of playing with the geometry parameters that are the geometry that we are trying to do the lithography of consists of. And basically, we observed that, for example, for alpha tilting, alpha is the tilting of the facets. For alpha values until up to 20 and so degrees, we have reliable patterning of the PPA layers, while for higher degrees, we start having feedback problems and issues until complete feedback divergence for 30 and above degrees. And this is valid for fixed values of periodicities. But the point is that we have to take into account that the thermal scanning probe lithography, of course, relies in the use of a hot nanoprobe, which has conical shape and hence has some intrinsic limitation. And we can ease the patterning process, for example, by allowing easier configuration, easier geometries, and for example, allowing wider spacing and wider periodicities. And by appropriate change and variation of these geometry parameters, we were able to achieve steeper facets up to 35 and so degrees. So given the fact that we are able to fabricate these faceted nanopatterns, how do we exploit them to work with the material and to induce strain and observe the effects of the strain onto the layers? So we started exfoliating and transferring flakes of different thicknesses using a custom setup that was built by another former PhD student, Michele Ceccardi, in our department, and which allowed us to use an optical microscope along with a two-component alignment components, which allowed to align a PDMS sustaining a flake to be transferred on top of a substrate. And also, by the use of tilting components, we were able to control the wavefront of the PDMS respect to the position and the direction of the ridges of the facets that we defined by grayscale lithography. So in this image, it's shown the result of this kind of exfoliation process. And here you can see the presence of two monolayer of MOS2, two monolayer flakes of MOS2 that are indicated by this white dashed line, along with a thicker few layer flake in the central area. And the first interesting thing is that we notice that there is a high degree of conformality between the monolayer flake and the underlying pattern at the point that it is almost impossible to locate it by eye. And that is because, of course, we are talking about a less than 1 nanometer thick material that is lying conformally on top of a nanopattern that is around 60 nanometer high. And it is slightly more visible if we like exasperate the z-axis scale, and here we can recognize like barely the shape of the monolayer flake. And the fact that we are actually observing monolayer MOS2 is confirmed by Raman microspectroscopy, where we observe that the vibrational features of MOS2 lie in the right and expected regions, spectral regions, and also for the monolayer flakes, they present a spectral shift around 19 centimeters to the -1, so coherent with the presence of monolayer MOS2. So I told you that they are more or less conformal, but can we actually quantify the grade of conformality? Well, to this purpose, we plotted different line profiles extracted from different positions along the AFM topography image, and we compared these profiles with the profile obtained from a bare PPA after patterning with grayscale lithography. And we observed that the same peak-to-valley height that we observe on bare PPA is reproduced and observed again in the lowest part of the few layer flake and also on the monolayer flake, which is here. And the few layer flake is also interesting that we observe in this image because it has like a decreasing grade of conformality when we go from the bottom to the top part of this image. And as we will see, this is interesting for different reasons. So to start understanding whether there was some kind of strain-induced effect on the optoelectronic response of these materials, we tried to observe the photoluminescence coming from monolayer flakes that are lying on respectively flat and patterned PPA. And we observed that actually there is an enhancement of the photoluminescence coming from the strained flake respect to the flat ones, with an enhancement factor that lies between 2 and 3. However, the effects that we expect to observe are likely to be present at a higher resolution scale, since we are using and exploiting patterns that have sub-micrometer periodicities, and hence a micro-Raman spectroscopy like this is not suitable because it is diffraction limited and cannot allow does not allow us to observe these kind of very fine effects. So to overcome this limitation, we relied on Kelvin probe force microscopy measurements. And Kelvin probe force microscopy is an AFM-based technique, which is performed in tapping condition and which exploits conductive probes and exploits the conductive probe to be able to extrapolate, to measure the so-called CPD, so the contact potential difference. And this is actually related to the work function of the surface. And the work function of the surface is related to the CPD signal in this way. So basically, it's represented by the difference between the work function of the tip and the work function of the surface normalized to the unit charge. And also, I want to stress that this was performed with a single pass configuration, which means that at the same time, pixel by pixel, we are able to measure the topography signal and the CPD signal. So these two maps, for example, are co-localized. And the first interesting thing that we notice is that while in the topography signal, the presence of the monolayer is very hard to locate, it's very clear for the CPD image, where we have a very strong contrast between the monolayer and the CPD signal of the PPA. And also, if we plot an histogram of the CPD values extracted from flat regions of few layer and monolayer flakes, we observe two distributions that are more or less 240 millivolts distant, which is actually coherent with the difference, intrinsic difference in work function between monolayer and multilayer MOS2. So to try and understand sorry, it's stuck. Okay, so to try and understand if there is some kind of localized effect at a high resolution on the electronic properties of the flakes due to the underlying pattern, we started extracting CPD and topography line profiles in the two images. From the two images. And we started observing that there is actually a periodic modulation of the work function of the flake. And we observed that we have this periodic modulation with the same periodicity of the underlying pattern, and also we have a CPD dips, or we can say increase of work function that is localized in certain position. And we notice that they are localized not in the top of the ridges, not in the valleys, but on left facets. And the fact that this is a strain-related effect is also visible from this line profile of CPD comparison, where we compare line profiles of CPD extrapolated from regions with that possess different degrees of conformality. And we see that the presence of this CPD decrease, these CPD dips, are present only in the regions that are most conformal to the PPA facets, while they are basically absent if we consider regions where the flake is basically freestanding on top of the facets, like profile number 4 here. And a similar thing we observe on the monolayer. So, for example, if we compare line profiles in terms of topography and CPD from the monolayer MOS2 flake, we observe that again we have CPD modulation that is in line with the underlying pattern, so with same periodicity. These modulation are around 130 millivolts, and again they are localized on left facets of the patterns, which is weird because we are patterning facets that are intrinsically and by design symmetrical. So why are we observing something asymmetric with respect to the single facets? And the explanation that we devise for this effect is that basically when you transfer the flake through the PDMS, you are giving directionality to the transfer. And this means that it should not have any effect on a flat surface, but in this case we are exploiting a three-dimensional faceted grayscale defined surface with facets. And since our flake is coming from one direction on one side, it will be basically not presenting any kind of stretching effect, but on the other side, the PDMS will be deforming along the facets, and hence also the flake will be deforming and stretching. And after the transfer, it will be left with a localized strain on certain facets. So this is an already interesting result, which we were able to observe by Kelvin probe force microscopy. But the point is that can we exploit this effect? Can we do something? Maybe can we try and observe the effect when we create a proper metal contacts and electrodes? Does it have an effect on the junction, the semiconductor metal junction that we may create on it? So this brings us to the last part of this presentation. So that deals with the creation of tuned and semiconductor metal heterojunction with different behavior due to strain localized. So, so far we have talked about these faceted grayscale defined nano patterns, just like if they were just an expedient to induce the strain into the 2D material layers, which they are. But the point is that they are useful also for another reason, which is the capability to perform in a maskless, non-invasive approach nanoelectrodes fabrication. And this is achieved via grazing angle gold evaporation, which allows to confine gold in the form of nanowires thanks to the shadowing effect that is formed between one ridge and the other when you give a flux of gold with a certain inclination, in this case 10 degrees respect to the surface. And this is observed on bare faceted PPA, for example, from these SEM images after gold evaporation, where these bright lines represent the confinement of gold, and these dark regions represent bare exposed PPA that has been protected by this shadowing effect. And this is true for faceted PPA, but if we have conformal flakes on top of the ridges, we have transferred conformal flakes on top of the nanopatterns, we do the same, exactly the same thing on top of the flake. So we are basically creating metal nanowires, metal nanoelectrodes, without the use of further lithography steps. So this is a clean fabrication of electrodes on top of the semiconducting 2D materials. And if we observe again this configuration after gold nanowires deposition, we observe, again by Kelvin probe force microscopy, we observe actually this confinement of gold, which we observe, yes, from the topography image, but even more clearly from the CPD map. And here you see the periodic modulation of work function that is given by the alternation of gold nanowires and exposed PPA, which is represented by these darker regions. But the interesting thing is that now we have created metal nanowires that are lying on certain facets, on certain regions of MOS2. And this MOS2 is locally strained on the left facets. So basically, these metal nanowires are addressing portions of the flake which are differently strained. And this will have an effect on the nature of the junction that we are creating between the flake and the gold And this is more clear if we compare line profiles. Here in this graph, we compare the topography line profiles, but also the CPD line profiles that are extracted from this image after gold nanowires deposition, which is represented by this solid blue line, and the same CPD line profile acquired before nanowires deposition. And you can see that basically we can distinguish between two behaviors. Left type contacts, which are here indicated by the green dashed line, present absolutely no change in CPD values before and after nanowires deposition. And this is an indication of the fact that we have reached a match between the work function of gold and of MOS2, which results in the creation of a ohmic good quality contact. On the contrary, we see a critical increase of CPD if we compare the CPD before and after nanowires deposition on right contacts. And this, if we compare with other results dealing with Kelvin probe force microscopy on MOS2 gold transistors, is indication of the presence of a built-in electric field and hence of a Schottky junction. And so the point is that we have an alternation of behavior. So with this single nanowire deposition, we have an alternation of right and left contacts, and again of Schottky and ohmic junctions. And this is something that usually, when you work with semiconducting materials, you generally achieve this kind of control when you have the capability to use doping techniques, substitutional doping techniques in the silicon manufacturing. And of course, in the field of two-dimensional materials, substitutional doping is something that is kind of very difficult to operate, and hence to be able to reproduce something similar with an alternative approach such as strain is something that can be very interesting. So this is the end of my presentation, and I hope that I showed you some interesting results dealing with the NanoFrazor lithography. First, how we combine the thermal scanning prolithography with larger approaches for growing 2D materials to achieve replicable nanogeometries, nanocircuits made of MOS2. And also that grayscale thermal scanning prolithography can be a very useful tool for devising faceted nanopatterns that have the twofold advantage of inducing strain with appropriate transfer approaches, but also to confine gold on top of two-dimensional strain materials in a very clean way. And that these can allow us to kind of tune the nature, to change the nature of the semiconductor metal junction that we hence create. And okay, I'd like to, of course, thank my supervisors, Francesco and Marina, and also the other PhD students that collaborated to this work, and all the other collaborators. And of course, thank you for your attention.